Hello again. Last time we discussed where each trigonometric ratio was positive. We found that they were all positive in the first quadrant, only sine was positive in the second quadrant, tan was the only one positive in the third quadrant, and cos was the only one in the fourth quadrant. A handy way to remember these is to just remember cast. So whenever you're in an exam, it's very important that you draw this again, just a very small version of it as CAST, so that you can know all of them positive there, sine positive there, tan positive, and cos positive. It may be useful now to see trig reductions. So if we look at our Cartesian plane, we can represent that as 0 degrees in relation to origin, because if we were to draw an arm from origin, it would just be 0 degrees. If we drew an arm upwards, then the angle that it makes here would be 90 degrees, so we represent that as 90 degrees. Similarly, if we draw an arm that way, that would now be an angle like that. So that would be 180 degrees. And you can show the same for this one to be 270. And this, again, if you think about it, it's a full revolution. So it's also 360 degrees. So 0 degrees or 360, however you'd like to look at it. With this in mind, and using our handy cast diagram, we can use this diagram to find trig reductions. So we know that this will be 360 or 0, but I'm going to write 360 for reasons you'll see in a moment. 90 degrees here, 180 degrees here, 270 degrees here. You can see it goes up in 90-degree increments. So in this quadrant, we'll just represent an angle as theta. However, we always want to get an angle to be reduced into this sort of quadrant. So we want theta to be acute, so less than 90 degrees. Or even if it is 90 degrees, that's also okay. So we want theta to be acute. So in order to get that, we need trig reductions. If our angle happens to be in the second quadrant, the sine quadrant, then we'll use 180 minus theta. If we have it in the third quadrant, this quadrant here, we will have 180 degrees plus theta. In the third quadrant, we can have one of two. We can have 360 degrees minus theta, or we can simply represent it as negative theta. So, as I mentioned that theta will be acute, it's easy to see that 180 degrees minus some acute angle theta will give something between 90 and 180. Hence, we get an answer in this quadrant. The same applies for this quadrant, the third one. If we take 180 plus an acute angle, acute being less than 90 degrees, we'll get something between 180 and 270. And the same for this quadrant. So that's why we use these reductions. So that's all well, but that's just theory. How does this apply? Well, let's give ourselves a problem. If we had sine of 135 degrees, how will we find the value of this? Take a moment to try it yourself, and then come back when you have your own answer. So, our first step is to draw our cast diagram. Then we just roughly write our angles here. And we decide which quadrant will 135 degrees be in? Okay, so I can see that this is definitely less than 180. And it's definitely more than 90. So from here, we know that it's going to be in our second quadrant, over here, the sine quadrant. So what reduction do we use? Recall that in the second quadrant, our reduction is 180 minus theta. So we have to show 135 degrees to be equal to sine 180 minus some theta. Now we just do some simple arithmetic to find what theta is. And we can solve for theta equals 45 degrees. So now that we have our theta, we can plug it in to this equation. So sine 135 degrees is equal to sine 180 degrees minus 45 degrees. Now, recall that sine theta is going to be positive in this quadrant, the second quadrant. We discussed that in a previous video. So what this means is that once you've got your theta, your reference angle, you can simply rewrite this as sine 45 degrees. That's why reference angles are so powerful, because we may not know the value per se of sine 135, but we can certainly reduce it to the sine 45, and we know the value of that. Recall we can use our special triangle with 45 degrees, and 90 degrees with those lengths, and we can find sine 45 degrees is equal to 1 over root 2. So let's try one more example quickly. What about cos 135 degrees? It's the same angle. It's the same angle, but we're going to be using a different ratio, namely cos instead of sine. So how do we do this? Again, first step, we draw our cast diagram. We write our angles here. And we decide the quadrant. We can see that, again, 135 degrees is between 90 and 180. And that fits perfectly into this second quadrant. So we will write cos 135 degrees is equal to our reduction for that quadrant, which, as you'll remember, is going to be 180 minus theta. We can again solve. We can say that 135 is 180 minus some theta, and we can find theta to be 45 degrees. After this, we write that cos 135 degrees is equal to cos 180 degrees minus 45 degrees, and we write cos 45 degrees. However, something's missing here. This is true. Our reference angle is certainly 45 degrees, as we've proven in 1. This is what I'm referring to as 1. And so we can see that our reference angle is correct. But if you see here, we're working in this quadrant here, right? And we've agreed that sine is the only ratio that's positive in that quadrant. So if we use a reduction in this quadrant for cos, we have to use we have to say negative. So I hope I haven't lost you there. Just to recap, if we have sine working in the second quadrant, we use the reduction for the second quadrant, and we get theta to be 45 degrees, and we just say sine 45 degrees because sine is positive in that quadrant. However, when we get to cos of 135 degrees, it's still in that quadrant, so we still use that reduction. However, we have to say negative cos 45 degrees. Because if we just say cos 45 degrees, you can see that 45 degrees, because it's acute, it'll be in this quadrant, and it'll give us a positive answer. So cos 45 degrees will be positive, right? So that's a problem, because we know that it's got to be negative since it's in the second quadrant. So we just simply put a negative sign here. I'm going to give an example for the fourth quadrant, because we could call this 0 degrees, which would make this angle just negative theta. That would be the reduction. Remember, we discussed that. So, because it would just be the reasons quickly say, it would just be measured counterclockwise clockwise from the x-axis, whereas we usually measure the angles counterclockwise, that way. So that's why we get negative theta there. If you want to check that, if you have a calculator on you, check that this is equal. You can plug in any value of theta that is acute, and you will get this to be true. So if you want to check me, if you don't believe me, feel free to do that. I encourage you. So here's my question. If we have tan of negative 45 degrees, I like 45 degrees if you haven't noticed, it's a special angle. So if we have tan of negative 45 degrees, what do we do here? Because we already have that tan is going to be acute. We already have that tan is acute. Okay, so let's just do this systematically, same way as we did the rest. We draw our cast diagram. And we just decide which quadrant it's in. We already discussed that it would be in this one, because it's negative, so it's measured clockwise, whereas we usually measure counterclockwise. And it's acute, so it's got to be between 360 and 270, because this would be the same as tan 360 minus 45 degrees. Okay, so we have tan of negative 45 degrees. We already have our theta, and we know which quadrant it's in, namely that quadrant there. What do we do now? Well, we just decide that tan is going to be negative in that quadrant, so we simply say negative tan 45 degrees. And similarly, you would do the same thing for sine of negative 45 degrees. And for that matter, you can do it for really all theta that's acute. You can say that tan or sine of negative theta is equal to negative tan or negative sine of theta. But when it comes to cos, this is cos's home quadrant. This is where it stays. So it has to be positive there, just like sine is positive here. So cos of negative theta is going to be simply cos theta. You can check me if you'd like. You can plug in, if you want, we can do an example here. If we have a triangle in the first quadrant, again, I'm going to use 45 degrees because it's just the easiest one to show, but you can do this with any angle you'd like. We can see that cos 45 degrees is going to be 1 over root 2 because it's the adjacent over the hypotenuse. Now, if we do the same thing for the fourth quadrant, we have 1, but notice that this will be negative 1. This is root 2, 45 degrees, 45 degrees, and a right angle there. So now we can just see that that is the adjacent, that is the hypotenuse. So we write cos 45 degrees, adjacent over hypotenuse, which is 1 over root 2. So you can see that our two results are exactly the same. However, I didn't write this correctly. It's negative 45 degrees because it's measured clockwise there. So we can see that cos 45 degrees is equal to cos negative 45 degrees, and that's where this result comes from. Over here is just a short general list of reductions. These are the ones for sine theta. These are for cos theta. And these are for tan theta. So you can see when sine, tan, or cos will be negative or positive based on the quadrants that they're in. And you can really derive all of these from the examples that we did earlier and more examples using different quadrants. But in general, this will be very handy to know if you're ever looking for a good quick reduction and you're stuck with a weird angle like 225 degrees, then you can see which reduction to use, and you can see whether your ratio will be positive or negative in that quadrant. I hope that you found today's video helpful, and as always, if you have any questions, feel free to leave a comment or send me an email. I would be more than happy to help, and I hope you have a great day, and I hope that you learned something today.